Okay, so the last speaker of the session is Filipe Rodrigues. Thank you for being here.
Good afternoon, everyone.
Yes.
Okay, should be fine now. Okay, great. No, yeah, I can hear the echo. So good afternoon, everyone. So my name is Filipe Rodrigues, and I'm going to present to you the work I've been doing for my PhD on Miguel Machucairo's lab, which is around dendrimers. So first of all, let me introduce you to the topic. What are dendrimers? So dendrimers are these highly ramified molecules with a very well-defined topology, and they can be functionalized on each of their branching groups, which makes them quite interesting molecules. And they can be classified by their building blocks, so to speak, the way they are constituted. So my work is going to focus on peptide dendrimers. And these dendrimers can be used for several things, such industry, for carrying drugs, they can also have antibacterial properties, but the thing I'm going to focus on is their capability for carrying nucleic acids. And since they can be constituted by amino acids, by being peptide dendrimers, depending on the amino acids, if they are titrable, they can be sensitive to pH, which is important for the internalization of the dendrimer, since they are somewhat large molecules. So it's going to be internalized via endocytosis, and then it needs to escape the endosome. And to escape it, pH plays an important role. So there was this experimental group that discovered these sequences, which an experimental group from my supervisor as well, and that discovered these peptide dendrimer sequences that can be used for effectively carry DNA and RNA. As you can tell, they are composed by lysines and leucines only, and they can pretty much differ. They can have this hydrophobic tail, which is important for the adhesion to the cell, and they can have the ones that we're going to study. They can have a tetraleucine motif on the hydrophobic core, or they can have two lysines, each palmitoylated as an hydrophobic core. Also, we're also going to study a sequence that is very identical to this one that was present previously, which is called MH18. And the only difference between these two is these four lysines, which are mutated to leucine. So this one, MH47, is slightly less polar. It's slightly less charged, actually. So these are the overall topologies that I just presented. Now, these are the main systems. And there are more than three here because we're also going to study different compositions of L and D amino acids. And why are we going to do this, you may ask? So we're going to do this because the group that discovered these sequences discovered that, well, if we change different combinations of L to D amino acids in some residues, for instance, if we change, for instance, residues from this sequence by changing only the lysines that are ramifying and making the branches, we can pretty much affect the effectiveness of the dendrimer. We can make them carry less RNA shown by this column. They can also input, they can take less RNA, and they can translate into a lesser effect. But there are other changes that can lead to better performances, and this is quite curious because we're only changing the chirality. So what is going on here? So this is the point that I just pointed out, that by changing L from a few residues from L to D amino acids can have a huge impact on their efficiency, which is weird. Also, even though I mentioned, if you remember, that they need to escape the endosome since they are internalized by it, the mechanism by which they escape the endosome is not quite clear. There are a few theories, but it's not really well defined which one is the right one. And since I also mentioned that the dendrimers, and if I didn't, I mention now that the dendrimers have a very well defined topology. However, regardless of this well-defined topology, which limits somewhat their structural variability, they also don't have a secondary structure like a protein. So they are still quite free. So it's hard to have experimental structures for these structures. So this is all of these points are points which can be covered by our computational approach. So we're going to pretty much study the effect of having different hydrophobic cores, as well as having different compositions of L and D amino acids. And we're going to study the effect of pH on these structures and see what happens if we have these structures on water. What happens if we have all these differences that I mentioned. So we started by building the dendrimers and parameterizing every other block, like the ramified lysines that form the branches. And then we needed to construct the dendrimer, and we used a particular protocol to make the dendrimer become completely stretched out in order to uniformize the bias associated with the way we build the dendrimer. And then the structures after initialization were then sent for production runs. So first of all, let's look at the charge of the dendrimers. What is happening to that? So we see that overall, I'm only showing less than half of the systems here for simplicity, because I don't really want to drown you with plots and plots and plots. So, but trust me that all of the other systems behave similar to this. So we see that their charge pretty much converges within 25 nanoseconds, actually in less time. So the charge is very well behaved. So it's no real surprise that when we look at full titration curves for the dendrimer, as well as the partial titration for each of the generations, each of the levels of branching, we see that all systems behave quite similarly. There's this small deviation here from it's actually not a small deviation, it's for charge deviation from MH14. If you remember well, it's the structure that has 4 less lysines, which are mutated to leucines. And even though it seems that okay, it may be different despite the error bars being quite small, here we see that all systems have a very identical shape. But they have a very identical profile in terms of protonation. Now let's think about it. We saw the charges. Now what is happening to the structure in water? Since, as I said, they don't have a very well defined structure, we can't really measure secondary structure for these dendrimers. The best way to actually measure their overall structure is through the gyration radii, since they actually acquire a slightly spherical shape. So gyration, the radius of gyration captures perfectly their structure, the overall structure. And we see that this property is not so well behaved as a charge. We see that there are some replicates that it's really a stretch to call these for instance these systems equilibrated, and they're not converged at all. However, regardless of this, we see that when we look at when you look at the gyration of radius of the radius of gyration over the pH, we see that overall all their structures, they behave the same. There are some differences that are perhaps statistically significant. There are differences here, such for MH47, but we see that on higher pH values, they tend to pretty much converge to the same plateau, and it decreases. And this is quite easily explained due to them being composed by only lysines which are titrable, so they are only positive. So when pH increases, they deprotonate, which makes so that there are less charge, not perturbation, but the charge decreases, so there are less charge repulsion, so they are more allowed to collapse. Hence the decrease in radius gyration. And since we weren't really able to see that many differences between the systems, we actually tried to really find the differences by doing the radius of gyration over the RMSD on these scatter plots. And we see that overall, there are no differences. We can't really find different clusters or anything like that on lower pH values, which are have higher radius of gyration, they are more stretched out. But when we increase the pH, namely for pH 12, we see that for some systems it's possible to start to see small different clusters, which maybe we can start to find some separation, and the separation is pretty much due to the way the dendrimer collapses. There are some sequences that are allowed to collapse in, so the dendrimers have 8 branches. They are able to collapse in a 4x4 way, and for others they are able to collapse in a 6x2 way. It's only a slight difference in terms of how they collapse. Now, for water, this may not be quite that interesting, but if we consider interaction with other chiral molecules, such as lipids, we can see that it may be different. So now we're going to study membrane interaction for the dendrimers. The way we set up the system was pretty much, we started with the dendrimers far away from the membrane, such so that we allowed with unbiased MD for them to get close to the membrane, not to the point that they are completely like smashed over the membrane, but to a distance which they are starting to see the membrane. And then we cut the number of waters, such to guarantee that there are no periodicity problems regarding the dendrimer seeing the other side of the membrane over here. And then we went for constant pH calculations, since it's really nice to be able to cut a little bit of the waters to decrease the computational cost. So now for the dendrimer with the membrane, what is happening to the dendrimer? Is it actually getting close to the membrane? We can see that overall it is, and it converges within like 50 nanoseconds. But there is a important detail here. If you can notice, the blue lines and the red one, the red lines, they tend to be a little bit more down than the other ones. We can see that the green ones and the yellow ones, they're a little bit further away from the membrane. We see that they all adhere overall, but there are differences over the pH, and we see that for high pH, they tend to only adhere to the surface of the membrane, and have shapes such as the one previously. They are more stretched out over the membrane. And for lower pH, we see that they can insert a little bit further, it seems. This is a frame representative from this replicate. And we see that it's a little bit more compact, and it's a little bit more deep inside the membrane. It's actually starting to be inserted. Now, what is happening to the membrane? Is it being deformed by the dendrimer? Well, obviously it is. But we also see another important detail that, again, as we saw before, for lower pH values, the membrane tends to deform a little bit more compared to the higher values of pH. And this is actually somewhat to be expected, since as we saw, they insert more. Now, regarding the radius of gyration, what is happening to the dendrimer itself? How is its structure? And we see that overall, when compared to the same system in water, by these more deep colors, we see that overall the dendrimer is always more. It's actually more stretched out than in simulations with water, as we can tell here. These are the simulations with water. These are the membrane, and we see that they are more stretched out. And actually, their sphericity is actually lesser, so they are more stretched out and less compact. Even at pHs where they were, as we saw here, we could see a decrease, a more easy to follow decrease with pH on their radius of gyration. And we can still see that, but the value is always higher than the one in water. And their sphericity is also less, they are less spherical. So their structure is indeed affected by the membrane. And also, regarding the protonation profiles for the dendrimer, so what is happening to their protonation? Now, we can see that for instance, for the generation 2, which are the lysins which are a little bit more inside the dendrimer structure, we see that it is indeed affected by the membrane. So the more it is inserted, the more it goes towards here, we see that the more the dendrimer deprotonates for the pHs that are still protonated when it starts. They all start protonated, but then to deprotonate at higher pH, which is somewhat to be expected. And regarding the side chain now from the outer lysins, we see that the profile is somewhat identical. As it gets further inserted into the membrane, it tends to deprotonate more, but notice that only the high pH values are titrating. Now, when we look at the N termini, we see that this is the group that is actually really titrating on the pH range we chose. We see that for all pHs, they are actually getting deprotonated as they get closer and more inserted into the membrane. So overall, we were able to see that there are no meaningful differences in their structure in water for the dendrimers. Only slight differences in terms of how they tend to collapse. And even if this may not be that relevant in water, we saw that the dendrimers in membrane, they adhere to the membrane, and they are affected differently by the pH when they adhere to the membrane. Now, regarding future work, we're going to study the dendrimers now with nucleic acids, since, well, we want to study how they actually transfect nucleic acids. So it makes sense to study that. And for that, we need to actually study the dendrimers in amber, since the parameters for nucleic acids are slightly better from what I've read in amber than in charm. And last but not least, want to just acknowledge my supervisor, the whole MMS group, as well as my other supervisor, Ms. Darber, that is not here, as well as all of you for listening. Thank you.
Okay. Any questions? I have Natalia. Yes. No. Wait for the mic.
So I wanted to ask you if these guys form on their own.
No, they are not natural. They are synthetic. They're not naturally occurring structures in nature.
Thanks.
Thank you.
My question is, I noticed that we have done 200 nanoseconds, was it?
Mm-hmm. Yeah.
Time. And some replicates, I guess. I'm not sure. Yeah. That's, as you know, these molecules, they can take a lot of time to sample the conformational space, right? If you try to, I don't know, to estimate how bad is the undersampling. I'm asking this because when I did stuff with these guys, we went to the microsecond range.
Okay. Okay. Our hope for only using, and the reason why we're confident only using 150 to 200 nanoseconds is because the dendrimers, their overall structure, they pretty much only stretched out and collapse. That's how they behave. They are pretty much a sphere in water. That is, they are pretty much a sphere that only collapses and extends. And regardless of we being able to see that, okay, it's likely that we're not having the systems converge nor equilibrate nor anything close to that here. So sure, there likely are sampling problems if we think on those terms, but when we collapse, and this is using the last 100 nanoseconds of our simulations, regardless if we have 150 or 200, we see that pretty much the error bars, they all touch each other. The only exception to this is for MH47. And even if they didn't touch each other, and making their differences. Oh, sorry, making their differences less statistically significant. We see that their overall behavior with pH is identical. So we're pretty confident that we may have sampling problems regarding, okay, not really sampling completely, but it's enough.
Okay. Just out of curiosity, when you showed the RMSD measurement, how did?
That's a really important part for RMSD, for everyone who was not really seeing the detail, is that if we, let me just take you back to the slide that shows, okay, if we see here, the dendrimers they are not completely symmetrical. For instance, this branch and this branch is not completely symmetrical since the ramifying element is a lysine. So it's branching on the end terminus and the side chain. And the side chain branch is slightly longer, but there's still some pseudo symmetry here. And the thing about the RMSD calculation is that it places a number on the atom. So it may happen that the dendrimer actually needs to be turned around. This branch needs to be on the place of this branch for the true value of the RMSD to be completely captured. So in order to do that, we need to do the so-called permutations, which is exactly this, switching one arm to another in terms of the atom numbering in order to calculate. And just for reference, for these third generation dendrimers, we need to calculate 128 combinations per frame to actually be able to capture the true RMSD value, the lowest RMSD value. That's just one of the tricks.
Yeah, I was just asking because I was not sure if you decided to keep this way of doing or whether maybe you had found that it was not necessary for these cases or something like that. Okay.
For these cases, it is quite necessary.
Okay. Thank you.
Thank you.
I have a question actually. So dendrimers are used as well as aptamers, for example, for binding many things.
Yeah.
Do you know how they compare? Have you ever read anything about how they compare in terms of potential capabilities of binding to protein targets? If there is a comparison.
For binding to protein targets, I've only read. I have to be truthful. I don't really, not quite aware if they can be used for actually binding to proteins, but I know that they can be used for industry. They can be used as catalyzing agents for binding like iron or other metals and be used in catalysis. So it's likely that by modifying their composition, we may be able to achieve some form of, not like an immunoglobulin or something like that, but be able to actually bind to proteins.
Yeah, they have been used by some group to as a synthetic alternative to antibodies or antibody fragments.
Okay.
Juni?
Yes. So if I understand correctly, your computational studies find no difference between original peptide and L2D L2D substitution variant in terms of the structural ensembles of free state, right? So the difference in the affinity for nucleic acid should arise from the bound state, right?
Yeah,
so
exactly.
What kind of difference do you expect? That's my first question. And
Okay.
the second question is, okay, in terms of delta G, how different are they? Between the original peptide and L2D substitution variant. Is it something you can easily address by your computational method?
Okay, so let me address them in order. The first question was, sorry?
Oh, it was about the difference in structure ensemble in the bound state. What kind of difference do you expect?
What I expect in terms of difference in bound state. Okay. We expect something that goes something along these lines. We expect that there are some sequences that are going to be less able to bound, so their binding constant to the nucleic acid, it should be lesser. So since we don't really see differences in terms of how they behave in water, and the differences we saw in membrane, I don't think they justify this. So it's likely that we're going to see differences that follow this line. Alternatively, it's likely that, and I've also read that there are some papers which they show that, okay, dendrimers have a secondary structure, and when they jump to molecular dynamic studies with only one dendrimer, and even if it starts with like a helical structure, it completely loses it like on the start of the simulation. So it's likely that in competition for our approach, it's likely that if the property is dependent on not a complex, but if it needs several dendrimers to be binding to the nucleic acid, then we won't be really able to capture these differences. Our hope is that it's not the case, and it depends on one dendrimer. It doesn't need to have like a secondary structure of an ensemble of several dendrimers. And covering the second question.
The question is about delta G between the original peptide and L2D substitution.
Okay, if we expect to have different delta G from an L dendrimer to a complete D substitution, I dare say that it would also follow these lines, since we saw that, and that's the thing that we're really curious about, is that we see that every time when we completely substitute from L to D amino acid, we see that the properties all increase. But there's this detail that the efficiency doesn't really increase, regardless of the dendrimer being able to bind more DNA, in this case it's siRNA, and being able to transfect more nucleic acids to the inside of a cell. We don't really see the effect. So it's possible that we may see see differences because it's able to bind more, but it's not really able to pretty much lose it, or it's not able to escape the endosome, one of the two.
Thank you.
Oh, I'm just taking the cue, and I will also try to add a little bit of what Filipe just answered. There's a key point, right? In water, they should not be different. So fully D, fully L. In water, they should just be a mirror image. So all the properties should be the same. We are kind of counting with that. That's when we look at all these differences, we just assume that they don't. Of course, if you start to do just selective LD, then we could see differences, of course. But the whole thing is that when we look at this table, the experimentalists, they just don't know why something that binds better, sometimes they don't behave better in the end. There's a lot of unknowns. And I don't think it's the computational people that will answer this puzzle, but we will expect that when we start binding membranes, you start to see difference, because L and D, the moment you have chiral, you need chiral, right? So you need to bind something that is chiral, like RNA or DNA, or even lipids. But lipids, they kind of move around, so they are slicky. But with the nucleic acids, we do expect to see differences. And if we have enough, if our error bars will be small enough, we might see that difference. And to address maybe your second question, I think that our error bars will never allow us to actually answer what you are asking, because most likely, unless it's very, very clear in the structure, but if it's only several things, it will get lost. And even if we use the best methods to estimate the binding free energies, we might not get an explanation for this. But at least we try. And like I was saying to Marilyn before, if not us, who's going to do it, right?
I got curious when you said that they would have to be the images of each other. Is this one of those cases where you actually get just a mirror image. I don't remember my stereochemistry so well, but sometimes when you have several chiral centers, you actually have different molecules depending on the arrangement of the molecules. So my question is, the whole molecules are really mirror images of one of the others?
Yeah, for instance.
Oh, because they are completely substituted. Okay, okay. No, that one, that one true. Yeah, you're right. But for the other ones is not immediately obvious, is it? Yeah. Okay.
I don't know. Okay. It's substitutions on residues from the last generation. It's substitutions on residues from the first generation. It's substitutions on the residues in between. There's also a variation that we define ourselves that wasn't really present from all the combinations they had, which is alternating. For instance, the last generation and the second generation are completely transition, so to speak, to the amino acid, while the others remain L.
Yeah, but it's always replaced one full generation, right? Because of the synthesis, right? Yeah. I remember that now. Yeah. So okay. Yeah.
So Vic, I'm not going to remember all of this, but Vic Nanda and Paul Fakowski actually thought about D and L in terms of why one is, what we have in the current amino acid. And they basically said the thermodynamics, if you have all L or all D, they're all fine. But but basically if you try to mix them, you lower the stability. And so that's something to think about.
Okay.
Well, that's, if I may just add something to that point, is that the reason why we're studying with L and D amino acid and combinations of that is that actually it increases the degradation. It actually decreases the degradation. Sorry, it's the opposite. So it helps. It makes them be more stable when in the body. So they're less degraded. Since they are amino acids, they're less subject to proteolytic activity.